Okay, today we are going to learn some spectral theory about linear operators. So it's about the spectral or spectrum of linear operators. Okay, so this is closely related to remember that when you learn linear algebra, we have a matrices, and for a matrix you can consider the eigenvalues and eigenvectors, and this is quite similar to that because right now linear operators is like a generalization of matrices for finite dimensional cases. Okay, so linear operators are generalizing that to infinite dimensional spaces, but we can still consider the eigenvalues. And this whole lot of theory is called spectral theory, and it is much more complicated than the finite dimensional case or for matrix cases. So today we're going to just talk about some elements of that. First, we discuss a slightly more general setting called the Bana Algebra. Okay, here's the definition. So we start with the normed algebra. So it's algebra with a norm. So we use the notation L with norm. This. Okay, and the algebra itself is associative algebra. That means you can do a summation or multiplication between elements. At the same time, you can do some scalings. And the associative means that you can associate the constant or scalar to any of the variables when you make the multiplication. So let me write down that what that means. So let's say the L itself is a unital associative algebra. So that means you can define, you have two elements A and B. You can define A plus B. You can define A times B. And it is a Abelian group under the summation, but it is only a standard group for multiplication. That means the A plus B is equal to B plus A, but A times B, or the product of A and B, may be different from the product of B and A. So you think those as matrices, think A and B as matrices. And you can also do some scaling of that. So you can apply scaling, say constant C to A. Excuse me. CA times B. So you can multiply A, B together first and then multiply C. But you can also apply C to A first, and then multiply that matrix to B. Or you can move the C around anywhere. Okay, so that's what the associative algebra is. But at the meantime, you also have the norm defined. Okay, so it's algebra over, let's say, slightly more general case that consider the complex values with this is the multiplicative unit. You multiply I to any element in L, you still get the same element. Such that, so the unital means that you have this I here, such that the norm of this I is equal to 1, and also you multiply A, B together, the norm of that is less than or equal to the norm of each one of them. Okay, for any A, B in L. Okay, so that's called a normed algebra. If this L is complete under the norm, then we call this L a Bana algebra. Okay, the norm is just like the standard norm we have, and we call it algebra. It's called a Bana Algebra. Okay, so example is typical example is, let's say we have a say Bana space X. Just like the ones we had before. And then you can see we can define this L to be all the linear transformations from X to itself. This is a Bana algebra. Right? And it satisfies all the conditions we mentioned above. It has the unit value. You can take a summation, you can multiply any two elements in here, you still get a linear transformation. And the norm also satisfies this, right? And we know that this is a complete metric space. Sorry, it's a complete normed vector space, which means it is a Bana space. Okay, it's complete under the norm, under norm in this space. Okay, that is the operator norm. Should we say that with the operator norm? Okay, so that's a rather general setting. Okay. So given algebra, we can talk about the inverse. So they are like the inverse of with respect to multiplication. So suppose you have, it's just like the matrix inverse of matrices. Now we have Bana algebra. Then what do we mean by the inverse of that? So let's say T is an element of Bana algebra. Okay, it's called invertible. If there exists some S, which is also in the Bana algebra, and usually we can write this as T inverse, such that when you multiply S to T on the left or right, it is the identity. Okay, and sometimes we also consider the left and right inverse. So if A times T is equal to identity, then the A is called the left inverse of T. And similarly, if you have TB equals to I, then B is called the right inverse of T. And a very important feature or fact is that when a matrix or when an element at T has both left and right inverses, then these two inverses are the same, and that means T is invertible. Okay, and the reason is, you know this probably from linear algebra, that if you know that A is the left inverse of T, then you know this is equal to AI, because I is identity, and then since B is the right inverse of T, so I know that I can be written as TB, and that is just by applying the associative rule of algebra. We can put these two together first, right? And then you also have the B, so this part is I. You have the I times B, and that's just the B itself. So in this case, you can see A and B are the same. So if left inverse and right inverse both exist, then they must be equal. Okay, and this means that the matrix T is invertible. Okay, but in general, the operator T, or element T. So in general, T may only have left inverse or right inverse. What this says is that only if they both exist, they must be equal. Okay. And also, it is easy to see that if you have T that is invertible, and you have u that is invertible, then the product of these two is also invertible, and that the inverse of this is just equal to u inverse times t inverse. Okay, and you can easily verify that by multiplying this to say ut. Oh, sorry, multiplying this to tu. Then you can see that when you have multiplied the tu on this, then they will cancel that, and you just get that. So that's what happens when we multiply this by tu. Okay, so if both are invertible, then the product is invertible. Okay, now we're going to give a simple fact. We know that from above we know that if each element or each of this is invertible, and the product is invertible. The question is, if the product is invertible, can we claim that both of these two are invertible? And the answer is yes, under one very mild condition. The condition is that if you have two operators or two elements in the Bana algebra, and the product is invertible, then as long as these two are commute, then you can claim that each of them, every one of them, is invertible. Okay, so if T and S are invertible, T and S commute, that means the T times S is equal to S times T, and TS is invertible. The product is invertible. So now you know that ST is also invertible because they are equal. Then you can claim that both T and S are invertible. Okay, so let's see why that's true. Let's say we just need to show one of them is invertible, the other one is easy, right? Because of their kind of symmetric. How to show T is invertible? As we said before, if we can show that both the T has both left and right inverses, then we can claim that T is invertible. And to see that, let's look at this. So on the one hand, I know that the TS, since this is invertible, let's say the inverse, let U be the inverse of TS. So that means if you multiply TS by U on the left or on the right, you should get the identity, right? You have also this. Okay, so by the associative rule, you know that this can be written as T times US. So this means that US is the right inverse of T. Okay, so on the other hand, let's look at this one below. So because, should be this. The TS is invertible and the U is the inverse of UTS. Okay, so the top is at T times SU. So SU is the right inverse of T. On the other hand, look at it below. Then we have the U times TS, but because TS they compute, so I can rewrite this as U as T. Okay, just exchange the order of them. And then the left one is equal to US times T. So this means that US is the left inverse of T. And this means that T is invertible. Okay? And since T is invertible, similarly you can show that S is invertible. Okay? Similarly you can show that S is invertible. Okay, so that's one simple fact. Another result is about invertibility for some t, or in the neighborhood for some t. Okay? Suppose we have some invertible t, then we can claim that if you perturb this t a little bit, so say t minus a, perturb it by a, then it is still invertible as long as a is not too large. And the condition is that a, the magnitude of a, or the norm of a, I should say, is less than 1 over the norm of the t inverse. Okay, or in other words, a belongs to the open ball centered at 0 with norm 1 over the norm of t, or with the radius 1 over the norm of t inverse. Okay, so this is pretty much like that. You have a non-zero scalar, and then you know that it is in the neighborhood. It's still non-zero value, and in that case, it is invertible. You can compute the reciprocal of that. Okay, that's a very crude analog, but it has similar flavor of that. So the idea is here is that if T is a matrix, you know that's also true, right? You can perturb invertible matrix a little bit, it will be still invertible matrix. And that can be generalized to elements in Bana algebra. So we're going to prove this. So to prove this, we first consider a simpler case where T is just identity, and we know that is an invertible element. So we first consider the case that T is equal to I. Okay, so in that case, T is I, then we just need A to be, so let's say the perturbation A just need to have a norm less than 1 over, or smaller than 1 over the norm of T inverse, but T is identity right now. So the T inverse is also identity, so we just need the A to have a norm less than 1. Okay, let me use another notation right here. I use B instead. So we claim I times B is invertible, where the norm of B is less than or equal to 1, which is 1 over the norm of identity. Okay, we want to claim that is invertible. And not only that, we want to also compute what that inverse is. And actually, the inverse is the inverse of I minus B is the so-called Newman sum, or Newman series of B, which is just the sum of this. Okay. Okay, so let's see why this is true. First of all, let's say I define this thing to be S. I want to claim that the S is the inverse of I minus B. Okay, and to show that, let's just look at the definition of S. If I want this thing to be convergent, I just need to show that it suffices to show that it's absolutely convergent. And that means if you can show that this, okay, from 0 to infinity, if this is the convergent series, then we can claim that S is something that in the Bana algebra. But this is less than or equal to the sum of B to the power K. And you know that this is because of the rule here, right? So if you have A times A, which is A squared, then this is less than the square of the norm of A. But if you have more of those, If k of them, you can have the same thing right here. But now you can see that if B has a norm less than 1, then this is a geometric sequence which is convergent. So for sure that is a convergent series, right? So that's why the S, or the series here, or series here I should say, must be convergent. And that means S is well defined. Okay, and now we just need to check if S is the inverse of B. And to see that, let's multiply B and S together and see if it is equal to identity. So this is equal to B times, according to the definition, is the k from 0 to infinity of bk. And then you have another B outside, and just becomes sum of k from 1 to infinity. But this is just the same as S, except that the first element is removed. The first term in the summation is removed, and that is I. So that's this. Okay, and now you can see that when I move the I to the left, the BS to the right, I'll get I equals to I minus BS, which is I minus B times S. So that means S is the right inverse of I minus B. And similarly, we can show that the S is also the left inverse of I minus B. You can show that this is true, right? Just by multiplying B on the right side of S. Okay, and we can show that is equal to I. So all these two together means that S is the inverse of B, I minus B. Okay, and that is the Newman series we mentioned. Okay, Newman series. Newman series. Okay, so that's for a simple case where T is identity. But what about the general case? We just know that T is invertible. So in this case, let's look at the T minus A, where T is a general invertible matrix. Then we know that the T, I can rewrite this T minus A into this form, right? Because when I multiply T inside, then I get back to the T minus A. Okay, so now I know that T is invertible. Remember that T is invertible. So I know if I want to show this is invertible, I just need to check if this one is invertible. Because that's invertible, then product must be invertible as well. But this, we know that from the previous result, as long as this term has a norm less than 1, smaller than 1, then it will be invertible. So now let's look at the norm of this term. The norm of this, according to the rule for norm, so this is less than equal to T, norm of T inverse times the norm of A. So now you can see why we need this A to have a norm smaller than 1 over the norm of T inverse. Because if that's the case, this will be less than 1. Okay, and from the previous result, we know that this, if that's the case, if this is true, then this will be invertible. And since this is also invertible, so the product of these two is invertible. Okay, so we can also compute the inverse for that if you're interested in. So I have T minus A. We know that it can be written as Ti minus T inverse A, right? And then we can do the the Newman series for this term. That would be T times the sum of T inverse A to the power K, where K is so I should say the inverse of this. Now, so let me do it this way. The inverse of this is equal to, let's say that's equal to T times I minus T inverse A, and then inverse. So I know that if the A satisfies the condition, then this must be invertible. So this will be I minus T inverse A inverse times T inverse. Okay, but remember that this one can be written as the Newman sum, which is this. Okay, from 0 to infinity, T inverse A, this is like the B above, to the power K, and then T inverse. Okay, so that's actually the inverse of that in general case. So as you can see, if T is identity, then this reduces to the Newman sum of A, which is the inverse of I minus A. Okay, so that's the some simple fact about that. So from this, you can see that if you have some invertible matrix, or sorry, invertible T right here from the Bana algebra, then so this is T. Then we know that in the neighborhood of T, and the radius here is 1 over the norm of inverse of T. And in this open neighborhood, not including the boundary, for this neighborhood, everyone in here is invertible. Okay, so that's what the result claims. That's what this says. Okay, so that's a very useful fact that you should know. Okay, now let's get back to the spectrum of linear operators we considered earlier. So now, as we said, if X is a Bana space, and then we know that the L we defined to be the linear transformations from X to itself, this will be a Bana algebra, right? And then we can further consider this set right here. For any element in here, can we get something like this eigenvalues, eigenvectors from that? Okay, so now let's say the X is a Bana space, as we mentioned. In general, we will consider complex Bana spaces because the eigenvalues could be complex valued. It could be complex value. And so I'll have the X. Then we also have maybe some D, which is the linear subspace of X. Okay. So for this chapter, we use this notation just to indicate that D is a subset of X. It could be a proper subset of X, or it could be X itself, since we need to consider something like if it's a proper set, a subset or not. So this means that A is a proper subset of X. Okay, we need to distinguish that a little bit, not as before, where we don't care. Okay, so now here we have this D, and we have the T. That is a mapping from D to X. I will assume it is closed operator, closed linear operator. Closed linear operator. So remember that closed means that if you have xk converged to the x, you have txk converged to y, then this too implies that tx equals to y. A linear is clear, right? So we assume that T is this closed linear operator. Okay, so this is indeed from X to X itself, but the domain of T may not be the whole X, may not be the entire X, but just a linear subspace D of X. Okay, so in this case, let's consider several possible or similar ideas of eigenvalues. So the first case is, let's consider the first case. So this is called the point spectrum. So it's a collection of complex values lambda such that lambda I minus t is invertible. Sorry, it's not invertible. Okay, the point spectrum. Which we use the sigma p. P means point. T, so that relates to the operator T we have. It's closed linear operator. It is defined as all these complex values, lambda, such that the lambda I minus t does not exist. Okay. Okay, so in this case, we call lambda an eigenvalue of t. Remember that for matrices, the eigenvalues was obtained. So you have t that is a matrix. Then the eigenvalues was solved from that. And this means that the lambda makes the lambda I minus t a degenerate matrix, right? And in this case, this lambda I minus t is not full rank, and it is not invertible, right? So the idea is similar to that. But now we're considering the general operator case. So in this case, what do we mean by the lambda I minus t is not invertible? So lambda I minus t, first of all, it is also a mapping from D to X. Okay, because t can only be applied to elements in D. So this means that the lambda I minus t applied to X, where X is in D, just means that it's lambda X minus Tx. Okay, and this is something in X now. But notice that this may not be surjective. Okay, so the image of D under lambda I minus t may not be the entire X, and we will consider that case later. But first of all, we want to see if it's injective. If it is injective, then at least we can make a one-to-one correspondence between D and its image. So the first case, when we consider the point spectrum, means that this is a collection of all the lambda such that this is not a injective mapping. It is not injective means that you may have two different values in D, say X and Y in D, but they're mapped to the same element in X. Okay, so there exists X different from Y. They're both in D such that lambda I minus t applied to X is the same as lambda I minus t applied to Y. But because lambda I minus t is a linear operator, so I can move everything from the right to the left. Then we have lambda I minus t times x minus y equals to 0. Right? And this we call it z, and I know that z is non-zero. So this will be equal to 0. That means we can find some non-zero element z such that lambda I minus t applied to z is equal to 0. Or in other words, the null space of lambda I minus t is not the zero trivial space. Okay, so there are different ways to describe this, but the core idea here is that if there exists a non-zero element in D such that the image of that element is equal to 0, then the lambda I minus t is not invertible. And in that case, lambda is called an eigenvalue. Okay, and corresponding to z is called eigenvector. But we're not interested in that. We only care about the values right now. So the collection of all the eigenvalues is called the point spectrum, which is denoted by sigma p here. Okay, so now let's consider the second case, which is called the resolvent. And we use the notation rho t. And this is a collection of lambda, the complex values, such that the lambda I minus t is does exist. Sorry, I should say this. This does not exist. Okay. This does not exist just means that this lambda I minus t is not bijective. It's not injective. Okay. So the rho t here is called resolvent, and that is a collection of complex values such that this does exist and it is bijective. is a bijective. So remember we mentioned before that lambda I minus t is a mapping from D to X. Okay. The inverse exists means that the null space of this is just 0. Okay. And if it's also bijective, that means if I have a one-to-one correspondence between D and X under this mapping, then we call this element lambda, or we call this value lambda a irregular value, and the collection of regular values is the resolvent. So this is called regular value. In comparison, we have the eigenvalues above. Okay, so that's the resolvent. If it's a finite dimensional case, if the X is finite dimensional and the T is just a mapping from D to X, then the T is either, so a complex value lambda is either in the point spectrum or in the resolvent. Right? You see, like in the matrix case, a complex value is either eigenvalue or not eigenvalue. Okay, so that's corresponding to eigenvalues. And if it's not eigenvalue, then that means lambda I minus t is invertible. And that's invertible for matrices. That just means that it's a bijection. Okay, but for infinite dimensional cases, this is we will have something even more complicated than these two, and that third one is called continuous spectrum. And we use the notation sigma. Since it's still spectrum, we use sigma, but it's continuous, so we use sigma c of t. And that is the collection of complex values such that the lambda I minus t still exists, but it's not bijection. So we know that it must be injective for the inverse to exist, but it's not bijective, means that it maps D to just a subset of X, proper subset of X. Okay, so in this case, the lambda I minus t applied to X is just a proper subset of X. Sorry, this should be D. Okay, but this proper subset is dense in X. That means if you take a closure, you will get the X. So although itself is only a proper subset, but you take the closure of this image, it becomes X. In this case, the lambda is in the continuous spectrum. Okay, so that's one case. And there's also a case we call the residue spectrum, in which case, so here we have sigma r of t, and again it's a collection of complex values where lambda I minus t is again invertible, but that means it's lambda I minus t itself is injection or injective, and in this case, even the closure of lambda I minus t, the image of D under the lambda I minus t is not equal to X. So it's a proper subset of X. So that's the last case. So for infinite dimensional cases, these two scenarios may also happen. So the lambda could be these two as well. If it's only finite dimensional, X is only finite dimensional, then only the first two can happen. Okay. So that's the definition for them. So now you can see that the whole plane, the complex plane, can be decomposed into the union, or disjoint union of the four cases above. So this rho t, remember that is called the resolvent, and then you have the sigma p of t. This is a collection of eigenvalues. Then you have the sigma c of t. This is a collection of lambda such that this happens. And then lastly, you have the sigma r of t, which is the last case. And the union of these three is called the spectrum of t. So we use just the sigma of t. is a collection of, or is a union of them. Spectrum of T. Okay, so when we mention the spectrum of T, it's just the union of these three, or it's a complement of this resolvent. Okay, so these two are always complement to each other and then make this complete C. But the spectrum itself can be decomposed into the union of these three cases. And if it's finite dimensional, then these two must be gone, must be empty sets. But if it's infinite dimensional cases, both of them could be non-empty. Now we'll see the examples later. Okay, so that's the decomposition. So I want to make several remarks that you can see. So the first remark is related to the one I mentioned earlier. We say that the T, so I would say the lambda I minus T is invertible. Let me say in this way. So the lambda is in sigma P of T, which means that the lambda is a regular value. This means that this is the lambda I minus T inverse is bijective, right? And in this case, I should say in this way. So the lambda is in the union of rho T, the resolvent, and the sigma RT, and the sigma PT, sigma CT, and sigma RT. So in the first and the last two cases, so in those three cases, so I should say, sorry, in these three cases, we know that this exists. Okay, and if and only if the lambda I minus T, the inverse of that exists. Okay, so we said that this is just a mapping from D to its image, which is lambda I minus T times D, applied to D. So we know that this whole thing here is just a subset of X, but at least this makes a one-to-one correspondence between that. Okay, and on the other hand, we know that since the inverse exists, we know there's no way to find a non-zero I should say in this way. So this is corresponding to the case that where lambda I minus T applied to X is equal to 0 implies that X is equal to 0. Okay, so that's what we mentioned earlier. Or in other words, if lambda is in sigma P, its eigenvalue, then that just means that lambda I minus T inverse does not exist. And in this case, there exists some X non-zero such that the lambda I minus T inverse applied to X is equal to 0. And this just means that there exists some X non-zero such that Tx is equal to lambda X. And now you can see that lambda is like the eigenvalue if T is the matrix and the X is like the eigenvector. Okay, so these two are just complementing each other. So that's what one of the remarks I want to make. Second remark I want to make is about the case where lambda is in the resolvent or resolvent set. So lambda is in resolvent means that the lambda I minus T is invertible, is bijective, right? So this means that lambda I minus T from D to X is bijective. And that also means the inverse is bijective. Remember that we can still have a D as a proper subset of X. to make this a bijection, right? Because it's infinite dimensional cases, this is still possible. For example, you can make a one-to-one correspondence between all the natural numbers with all the even numbers. Although the even numbers are just a subset, proper subset of natural numbers, but still can establish this one-to-one correspondence or bijection. Okay, so that's what this means. And also, the question is, can we claim that the lambda I minus t and also the inverse of lambda I minus t are linear or are bounded operators? So it is clear that they are linear because t is linear. It's clear they are linear, but we need to see if they are also bounded continuous. We first can show that lambda I the inverse of lambda I minus t will be closed because t is closed. We can see that, we can then prove that the lambda I minus t inverse is also closed. And why is that? Say from t, for example, if I want to show that this thing is closed, I just need to show that if, say I have uyk converge to y, so this is in x, and I also have lambda I minus t inverse times yk converging some x. I want to show that the question is, can we show that lambda I minus t applied to inverse applied to y is equal to x, right? That's what we mean by closed operator. So to show that it's closed, we need to show this. So now let's say that the xk is defined to be that. It's defined to be this one. And then because it's defined to be this way, and since lambda I minus t is bijection, so I know that the yk is just equal to lambda I minus t applied to xk. And that's just lambda xk minus txk. Okay. So what we have here is that the yk converges to y, the xk converges to x, right? So this converts to y, this converts to x as k goes to infinity. So that means this will convert to, according to, because the both of these two have limits, so I know that this must convert to lambda x minus y. The reason is txk equals to lambda xk minus yk now. So since this converges to lambda x minus y, I know the txk converts to lambda x minus y. So that's one thing. The other thing is because t is closed, right? So t is closed. So if t, since t is closed, since we know that xk converges to x as we show in here, and I also know that txk converges to lambda x minus y. So this too means that the tx must be equal to lambda x minus y, right? Since t is closed, so t closed. We have that, and this means that y is equal to lambda x minus tx. And because lambda I minus t is invertible, is bijection, so I know that x is equal to lambda I minus t inverse times y. And that is what we wanted to show right here. Okay, and this shows that lambda I minus t inverse, the inverse of lambda I minus t is a closed operator. Okay, so it's a closed operator, and it's linear, and it's mapping from x to d. Okay, so if I want to show that this is continuous, I can try to apply the closed graph theorem, right? But I also need to check what this d is. Is d a complete, is a closed set or not? It's a subset of a complete space X, right? We know it's a subset of complete space X. So if you can show that D is closed, then D will be complete as well. And following the same idea, if we can, if you have the xk converging to x, and then since this is a bijection, I know that xk converged to x means that there exists some yk such that lambda I minus t inverse times yk should be equal to xk. Okay, if I know this convert to x, then similar as before, I can show that this will convert to something like lambda I minus t inverse times y. And this means that x is also in D. And then D is a closed set. So following similar idea, you can show that D is closed. And that means D is also complete. So now we have a closed operator and some mapping closed linear operator from x to D, and x is closed. So by closed graph theorem, this means that the inverse of lambda I minus t is in L from x to D. Okay? And because of that, we can also claim that lambda I minus d is also linear, is also bounded. This is by the Bana inverse mapping theorem, right? Because you have a mapping from x to d, and that's a bijection, and this one is a continuous. The inverse is also continuous. The inverse is just lambda I minus t. So this is also a bounded linear operator, which is from d to x. Okay, so in that case, you don't need to worry about that. When the lambda is in here, this thing actually is in L, x, d. Okay, it's a linear mapping from x to d. It's a bounded linear operator from x to d. Okay, so that's another remark I want to make. Okay, now let's look at some examples. The examples below just to show that the spectrum can actually all these scenarios may actually happen in practice, okay, for infinite dimensional cases. Okay, so let's look at the first example. We see that this could happen. Spectrum. So this is the case where we have a eigenvalues. So let's say we have an operator, and we try to find out the eigenvalues of this operator. So here, let's say the x is the standard L2 space, square integrable functions, Lebesgue square integrable functions. And we call this D to be a closed linear or just a linear subspace of x, and that is all the elements that are twice continuously differentiable over the interval 0, 1. They also require x0, x1 to be 1 and to be 0, right? And x prime 0, so prime 1 is also equal to 0. So this is my D. Okay, and then I define my D, my closed linear operator T from D to X as the second order derivative. That means the Tx, where x is from D, right? X is twice differentiable function. I just define this to be negative x double prime. Okay, so this is the linear operator. And it is easy to show that it's closed. We showed something similar to this. If it's just a singular regular derivative, just first order derivative, then it is a closed operator. But if you do second order derivative, it's also a closed operator. And then we want to show the eigenvalues of this linear operator. Okay, so my claim is that the spectrum only contains the sigma p, which are the point spectrum, and this contains all the eigenvalues, which is 2k pi squared, where k is natural number or 0. So let's show why this is true. So first of all, we can find some, so for point in this, let's call this the set lambda. So for any lambda in, or I'll say, just look at this kind of functions. Sine 2k pi t. Let's define the xt to be this. Then you know that x prime of t is equal to cosine, should have constant outside, should be 2k pi times cosine of 2k pi t. And x double prime of t will be negative 2k pi squared sine of 2k pi t. So this becomes negative 2k pi squared times x of t itself, because this is essentially xt itself. Okay, so the left-hand side is tx. The right-hand side, the left-hand side is negative tx, because t is negative x double prime. So it's negative tx. The right-hand side is this. So that means tx is equal to 2k pi squared x. Okay, and this is like the lambda, right? And if x is cosine of 2k pi t, it's the same, but that just means that 2k pi squared is in the point spectrum. Okay, they're eigenvalues. And now let's just check what happens if lambda is not something like the square of 2k pi. And in those cases, we will show that they're regular values. And to see that, if, say, lambda is not in is any other complex value, it's not in lambda. So in this case, let's look at this equation, the t minus lambda x, lambda I times x. Just look at this, equals to f. Okay, so I want to show that this lambda I minus t, or t minus lambda I, is going to be a bijection. Right? To show that it's bijection, I just need to show that, first of all, it will be a how should I say that? It will be an injection, because if this applied to x and this applied to another function y equals 0, then we will be able to show that this will be we will get just 0. Sorry, if I say this applied to x, I get a 0, and t lambda, sorry, lambda I applied to y is also 0. This just means that t minus lambda I x minus y is equal to 0. But since the boundary conditions we have here, there is only a unique solution for this case, and the unique solution is 0. So that means x minus y must be equal to 0, and this means that x equals to y. So that this is actually a injection or injective, and to show that it's surjective, we just need to show that for any f in x, we can find some value x in D such that this hold. And the question is if this is true, if we can find a unique x such that this one has a solution for any f here. And the answer is yes. So for any f in x, so let's look at this equation. This just means that tx, t minus lambda I times x, is just negative x double prime minus lambda x equals to f. And that is this one has a unique solution. The reason is if you require the x to satisfy the boundary condition in D, then let's say we apply the Fourier transform on both sides. The Fourier transform means that you have a basis like this, 2k pi ti. So this is the ek of t is defined in this way. And the k is all the integers. So this is the Fourier basis. And then you multiply this, you apply this Fourier transform on both sides, which means that you take, say for example, f can be written as the sum of f and ek, as we did for Hilbert spaces, right? Because this is a Hilbert space, H. So this ek is actually a basis, a complete orthonormal basis for the R2 space, for the X, space X. And then you can decompose f into this way, and this is the Fourier coefficients, and this is just the Fourier basis. So you can apply this transformation on both sides, and then the left-hand side, right-hand side will get that, then you just need to match the coefficients on both sides. And by doing that, you can see that the xk, sorry, the xt, which is the x here, the xt actually has a unique solution, and that solution is this, sum of ck 2k pi squared minus lambda squared times the e2k pi it, or ti. So this is like the ek, said. Okay, so this is like the coefficient, this is like the inner product of x and ek. This is for all the k. Okay, and this can be obtained by where the ck is this f ek. Okay, the Fourier coefficients. This is like the ck. Okay, so that's the property of Fourier transform. You apply the Fourier transform on both sides and solve for x, and then take the inverse Fourier transform, and then you get the solution x. And this is the unique solution for this problem. And that means this is actually a bijection. Okay, and this bijection means that lambda is in rho t. So as long as lambda is not in here, then lambda is in rho t. So that means your space or your complex plane is just decomposed into sigma pt and rho t. Okay, and this contains all the eigenvalues. It contains all the, which is this one, and this right here contains all the other values. That's one case. Okay, so now let's look at another example. This is pretty similar to the matrix case. So what happens if we have, we know that for infinite dimensional cases, we could also have other types of spectrum. So let's see, this example shows that we could have some non-empty residual spectrum. And in this case, let's say the x is the set of continuous functions over interval 0, 1. And let's define the t as a mapping from x to the x, and it maps any element x to t times xt. So say we have xt, that is a continuous function over 0, 1, then I just multiply by t again, and I've got this new one. So it is also in x. Now the question is, what is the spectrum of this t? Okay. Let's first look at a simple case. Say if lambda is not, so this is the whole plane, C, this is 0, 1. So if lambda is not in here, it's anywhere else, then let's check. In this case, lambda, say lambda I minus t applied to x will give us the lambda x minus tx, right? So let's see if this one is invertible. So let's apply this to sum x. And in this case, this is just giving us xt over lambda minus t. Okay, and as you can see, if I take the norm of this thing here, it will be just equal to xt minus lambda t. I would take the norm of that. That just means the maximum value for t between 0, 1 of xt minus lambda t. Lambda minus t, sorry. Right? But remember that lambda is not in here, so it's somewhere else. But it's, no matter where it is, it must have a positive distance from to this interval. So that means 1 minus lambda minus t. This must be bounded away from 0, and is bounded above as well, bounded above by some positive number, which is the distance, or the largest, which is the distance between a lambda and that interval. Okay, so that's something that we show that it can be bounded by the maximum 1 over lambda minus t, where t is this. And then we know that this is some number that is strictly bigger than 0, but also so finite times the norm of x. So this is indeed a bounded linear operator. This is actually in Lx. And that means the lambda should be in the row t, in the resolvent. Okay, so that's the case where the lambda is not on the interval. But what if lambda is indeed on the interval? Okay, if it's on the interval, then let's see that lambda I minus t applied to x, as we said, it's just the lambda minus t applied to x. So let's say I have tx. So the new function will be just the lambda xt minus t times xt. And let's see what happens if this is equal to 0. I want to check if this is a injective or injection. So I just need to check if this one only has a 0 solution. Well, if this is equal to 0, that means lambda minus t times xt. This must be, if we want this to be 0, then the xt must be 0, because lambda minus t is non-zero everywhere except at t. Except at lambda. So it's like this is 0, this is the 1, this is lambda. So we know that the x lambda minus t, so this is the t direction, is something like this, right? So lambda, this is what lambda minus t is. Look at the function value. Well, if this times xt is equal to 0 everywhere on this interval, and this xt is continuous, then the only possibility is that xt itself is a 0 function. And this implies xt must be equal to 0 for any t on the interval. And this means that this equal to 0 only has a unique solution, which is 0. And that means lambda I minus t is indeed invertible. Okay, it's a bijection. It's injective, so it's invertible. And now we just need to check what is the image of that. We check the image. I should say the D. We check the image. No, it's just the x itself, because D is such that x. We check the image. So we want to see if this is equal to x. If it's equal to x, then the t must be regular. But we already showed that. But the question is, right now we showed that how should I say this? There's no way that you can get, say for example, I have a constant function here. Let's say just constant function 1 in that space x. That means I have a function, this is t, so always taking value 1. This is my function. Can we find some other function x in here such that the question is, can we find the x of t, which is the continuous function, such that lambda minus t times xt is equal to 1 for any t? The answer is definitely no, because if t is lambda, there is no way to get a 1 on the right, right? So the question is, we cannot find such an x such that this is equal to 1. So that means the 1 here cannot be in the image of this. Okay, so 1 should not be, 1 is in here, but it's not in here. So that's why this is only a proper subset of x. Okay, so now we can only consider the last two cases, right? Because either this happens or this happens, because that is not a bijection anymore. We don't have this case. Okay. So the question is, which one of these is the case? So to see that, we just need to take the closure. We just need to take the closure of this set and see if it is equal to x. And the answer is similar as before. If we have a 1 here, there's no way to find the sequence of xk such that the lambda minus t times xk t convert to 1. Because for each of these xk at t equals to lambda, this is 0 on the left, and it is 1 on the right-hand side. And these xt's are all continuous. So lambda minus t times xkt should also be continuous, and they converge in the space x means that they will converge to some function I call it y, and that is also continuous. And it's a bit obvious, as I said, that the y at lambda must be equal to 0. So this y cannot be the constant function 1 there. Okay, so that means there's no way to find a sequence in this space such that they convert to 1. And that means this set is not dense in the X. Or that means if we take the closure of this set, it is still not the full X. It's still just a proper subset of X. Okay, so this means that the lambda must be in the residue. Okay, so the last case. Last example. Continuous spectrum. All right, and so in this case, we're having things similar to before, but the x is not the continuous functions, but it's the 0, 1, L2 of 0, 1. Okay, so larger than before. And the norm is changed as well. Change the norm for this. And then in this case, the t, again, is a mapping from x to x, and again, it is mapping x to t times x, xt. Okay, so map this function just by multiplying it by t. Okay, so in this case, let's see what is the spectrum of this t. And similar as before, if lambda is not in C, is not in on the interval. So this is again the C 0, 1. If it's not in here, then it might be somewhere with a positive distance to this interval. In this case, we can still show that lambda will be a regular value, meaning that we will have a the lambda I minus t will be invertible, and this is actually a bijection. Okay. But on the other hand, if lambda is in 0, 1, then we can still show that the 1 is not in here. So the 1 is not in the image of x. So we can still show this. But the question is, can we show the closure of this is equal to x right now? The question is, can we show this? So unlike the case before, we actually can show this is true. Okay, and the idea is that for any y in here, we can find a sequence xk on the left, so that for any y in x, we can find the sequence xk, which is also in X. And I'm going to define this xk to be, say, 0, 1. The lambda is somewhere here on the interval. Okay, and over this near this lambda, I'm going to get a small interval, and this interval, say lambda minus 1 over k, lambda plus 1 over k. You can use other values, but the point is that I'm going to have a small interval here, which we call the ek, and as k goes to infinity, this this length will getting smaller and smaller. It always contains lambda. Okay, so let's define the xk to be the yt times characteristic function of ek of t, and also I'm going to divide this by lambda minus t. Okay, just by defining my lambda xt in this way, and why I'm doing this is because right now I'm now going to take the value at point lambda, because this ek is this interval, so it will be 0 in that interval. So I should say complement of that. Well, this one itself is ek, but I'm taking the complement. That means over this interval, I'm just force it to be 0, xk to be 0, so that I will not blow up there. Okay, so that's the xk. And then with this xk, we can show that lambda I minus t applied to xk. You know, lambda I minus t is just multiplying lambda minus t to this xk. So this will be equal to yt the ekc of t, right? Be that. So now in this case, I'm going to claim that this will converge to yt, and apparently this is converging to yt in the L2 sense, because this is the L2 space. So in L2 sense, to show this, we just need to take the integral of the difference of these two minus ekc of t minus yt. Just need to take the integral, square this and take the integral from 0 to 1. And you know that when it is inside the ek complement, these two are the same. So this is gone, and then this is only equal to the ek times the, because over the ek, this one is 0, and I only have this one left, so yt square dt. But this converges to 0, since this ek has a measure going to 0. And that means this actually converges to that in the L2 sense. So that means that any y, we can still show that is in the closure of the image of this. So in this case, the lambda will be in sigma ct. Okay, so it's either in rho t or in sigma ct. So that's how we decompose this. Rho t union with sigma ct. Okay, so this is just the interval 0 to 1, and this is closed interval 0 to 1, and this is just everything else. 0, 1, and everything else. Okay, that's how we decompose it.